here x of 3 input, p of 3, and also f, h, q, r, this thing. Okay, in the parameter, the small q is already multiplied with this one. Okay, and then here we have to apply the commutator estimation. This will give you the x of 3, condition of 3, because here you have to use the z3. Here you have to input the z3. Here you use the z1 and z2 to initialize the state with covariance. Now, and predict this value for the next step. Now you have to update this value using the z3. Okay, so z3. So in the residue, when you find the residue, this is a z3. Okay, and this may have any dimension. So you have a take the for loop here. For loop I equals to 1 to n measurement. Okay, and this n measurement is the length of z3. So in the for loop you have to run to this common filter, because in the residue you have to subtract the measurement prediction. This is measurement prediction from here, from this one, but we don't know the length of the z3. So we have to run the for loop for the time of ith measurement in the z3. If you run once you have calculated the residue and other covariance and commutator gain, then you have ended. So this is I, because if there are 5 measurements in z3, then there will be 5 steps. Then this will be have a 4 by 5 vector. Then after this end, you have to apply the total probability theorem. Okay, to sum up these Gaussian PDF. Okay, we have already sterilized this thing, and you're going to go to previous lecture or videos and in a book. So here it will give you the sum up of beta x I k k and z k. Okay, so this is your final output. This is your final output. This will actually, and this is a weight which is multiplied to each step and sum up to I equals to 0 to for example there are mk measurements, then you have to sum up and multiply the sum up the product of the weight and the step to give you this response, to give you the final output. Okay, and similarly the P, because this is calculated for for the z of 3, so this is condition on the z3, z3, okay. And then here also summation r equals to 0, 1, mk measurement. Mk measurement is number of total measurement in z3. If there are 10 measurement in z3, then mk is 10. Then beta and okay, beta I and pk I plus minus, and then this term I k transpose, okay. This is whole summation, and then minus this thing x of k zk and x of k zk transpose z plus. This is formula. So then for the next time prediction, you have to use comma filter again here in this function here, comma filter prediction. This will input here, and then x of p of k zk, and f is used for transiting the these matrices to the next time scan, and q. So this will give you k plus 1, p, k plus 1, and condition on k plus 1. Okay, so if you are here 3, then this will give you the x of 3 plus 1 and 3 plus 1. Okay, similarly this one. Now your function end here. So your first recursion, which filter start from the scan of 3, is ended here. Then in the next scan, the flow will come to again here. The flow of the algorithm should have to come here again. It will take the scan number 4 and 3 and 4, because here first we will use 1 and 2. Okay, now we have to initialize with the scan number 3 and 4. Now next time the z2 will be z3, and this z3, and here row 4 and here 3. Okay, next time when you come here, initialization from scan 1 and 2 already done. Now 3 and 4. So 3 and 4, 4 is your position vector for the disk one, and 4 minus z3 divided by time is a velocity, 2 by 1 velocity for the disk state. Then similarly this is the fixed value. Then you have to use this protection here to get the here 5. Then this will give you the x of then this will give you 5 and So you have to remember that you have to update the predicted value of this thing conditioning on the new scan. Okay, conditioning on new scan. For example, first one you have to you use the 2 point scan number 1 and 2. Okay, and calculate the state and this one covariance and set this thing for the next time scan. For example, 3. Okay, for example 3, and then for example this one 3. This is mixed up with this one, this line. Okay, this value 3. Okay, 2 plus 1 3. So when here come here, then you have to update this value, this the predicted value of this one with condition of Z3. Okay, and the next time when you use initialize the Z4 and Z3, then set it for the scan number 5. Okay, scan number 5 here. 4 plus 1 5, then 5. Then next time when it come here, when the scan will come like 5, then you have to update this thing with this measurement 5 right here. Okay, okay. One and 2 will give you, scan number 1 and 2 will give you prediction of 3. Okay, okay, using the common filter prediction. Scan number 1 and 2 will give you the state of the 3 using the gamma filter prediction, using this term, this thing, and then scan number 2, because we initialize 4 and 3, but there is a missing 2 and 3. Okay, 2 and 3 has not been initialized, so we have to initialize each consecutive scan, 1 and 2, 2 and 3, then 3 and 4, then 5 and 6, then 6 and 7, like this one. So this will give you x of 4, okay. Then when you got this thing 4, then here update the scan number 4 using the z of 4, and then when update it, you will get the state of here 4. This will be output like x of I 4 4, and here also this will be like x of 4 z of 4, and this will like P4 z of 4. Okay, and then we have to predict this thing, and like this will become like x of 4 plus 1 5. Okay, this will be prediction of the scan number 5 using this formula. Again, when you come here, you initialize from 3 and 4. So this will give you prediction 5 5 5 5. Again, this is gamma filter. Then this will come here 5 5 and here 5. So those value which are already calculated here and those value which are initialized here, both value all together again input here to update with using the common factor estimation to update the x of 6. Okay, so as this is input here, then also this is also input here, this is also x5. You have to update x of 5 using the measurement z5. So also this is, will come here also. Okay, for the update. So in each scan you have to update this value, and when this value is updated at this position, then again you have to update this value, you have to predict this value and update this value using the same flow. So both value enter each other, means complete cycle, it's complete recursion. The 3 is predicted from here, updated here, okay, and this will give you the fourth prediction, fourth scan prediction. Then this value come here for again estimation for the next time scan, and here initialization of the 4th scan. This value is again input here, then again calculate the estimation for the scan number 4, the new initialized strike here. Okay, so you have to practice before the big exam, because your assignment have a lot of time, I know, 4 minutes, 10 marks, but it has 20 marks. Very important. 20 marks is very big marks. So if you start work on this from today, tomorrow, then you will see you have problems. Okay, then you have to come me, I will help you. Otherwise you will face many difficulty in the mid exam. Okay, but you can find the many solutions from the book, from the paper, like the chapter number 5 in the estimation to tracking with the application. This is the book that I recommend in your first lecture, and then chapter number 9 and fundamental of object tracking. This book is written by my professor, who was my supervisor in the PhD. My whole PhD research is based on this project in this book, because my professor whole life algorithm, he worked many algorithms. All algorithms are written here in this book. The pseudo code of all algorithms are written in this book. Okay, so there are many algorithms are already written in this book. So, and also the algorithms are written in this book. Okay, so these two books are, we will refer these two books in the whole semester, and you have to refer, you can say this is a guide book for you. You can find many solutions in these two books. If you have any problem, then you can go through this one in this book. In this book, chapter number 5, you can find how to use this thing. Okay, because the calculation of this state depends on the size of the Z tree. Okay, and this is again the calculated by the likelihood function, like we have already done. Z minus x equals to the maximum derivative of logarithmic, like something like this, is the maximum likelihood estimator like this one, and equal derivative on the first side and equal to 0. So this is actually 0. Okay. So this is actually this mean. So this is actually Z mean is equal to the average value of Z. The Z mean is equal to the average value of Z. Polynomial Z tree, then this is the average value of the average of the expected value of the Z tree. Okay, so we say that this is the measurement reduction. Okay, and we said this whole thing as a measurement innovation. Okay, any question?
What due date of mitigation? What due date of mitigation?
Innovation. Innovation means you are creating.
Due date of mitigation. April 20.
Can you come here?
Yeah. About deadline.
I understand.
Deadline.
Deadline.
Yeah.
Deadline.
About mitigation. Yeah.
Mitigation deadline. 1 week. But I'm not sure. Okay. But I'm not sure because I do not know the rule of the mechanism. So I will ask what is the duration for the submitting the assignment and the mid exam. Then I will when I upload the article and the paper, I will set the deadline. Okay. But if I have some flexibility, then I will give you maximum 1 week. Okay, because I have to set the grades on the 24th April. So because I have also some restriction to set the grade of the student in those deadline. So maybe 1 week is more. and at the same time you have to calculate the estimation error and also the trajectory and this mid exam and also assignment. Can I rough it? Rough? Okay, if you set the total runs, simulation runs for 100 for example, okay, then how this is the multi-color simulation run to check the the statistic test. Okay, whether you have correctly find the statistic of the algorithm or not. So how to do it? Suppose this is the and x of k. Okay, this is equation number 1. Okay, so what is this equation? You already know this equation from the last lecture. Or this equation, this is the error. This is the error. Okay, and this is the filter covariance, and this is transpose. Okay, T for transpose. So you have to check the output of this total probability theorem, this thing with this one, and check whether it satisfies the chi-square distribution or not. So you have to set parameter, suppose with the name of test equals to 10. Again, this is depend on your experiment. You can set with this value anything, because this value depend. This value, suppose this value is eta equals 10. This depend on chi-square distribution probability. Probability of false alarm. Okay, so you can test this thing, that the distance between the true value and the estimated value should be less than this value. If the distance, if this thing, determinant of greater than this test, and this is the false value. So you cannot use this value for calculation in the statistic test. You have to choose the only true value. You have to, if you, this is the okay. So again, this is the complete sentence. Inverse, transpose, this again complete sentence. So if determinant of this value is less than the test value, then this is a true track or true straight. Okay, so you have to check the output of each comma filter with this formula, okay, with the filter covariance. So with the filter covariance, and this is the inverse, this is transpose, this is the simple state. If this is less than, then the true track. If this is greater than test, then it will be the false track, because due to the variance, the distance is very far, so we cannot choose, because the false trajectory, this will be the false trajectory, this is a true trajectory. Okay, so again you have to set this value here, test for equal 10. So this value again, for example, in my case, when I perform an experiment in very small area, 5 meter to 5 meter, I set the test equals to only one value, because a small area. But if you have a bigger surveillance area, for example 1000 meter y-axis and 1000 meter at the x-axis, then set some greater value like 20, and also it depends on the velocity. If velocity is very small, for example 5 meter per second, then test will be 10, like this, because velocity, if you still set the 1 and velocity is very far, velocity is very high, 15-20 meter per second, then your trajectory will go far away. So then you can now test this value with the 1. Then you have to increase this value with the 20. Okay. Suppose in this book, my professor performed in the bigger area, like 1000 meter, so he used 20, because he used the velocity of the motion of target 15 meter per second. Okay, 15 meter per second with the maximum velocity of 25 meter per second, and he used this test 20. So again, it depends on the velocity and the maximum velocity of the target, and also surface area. If your surface area is bigger and the motion of target is high, then you can not choose this value. You can choose the different value, because your target position is depend on the velocity. If the velocity is high, then in each scan the position of the target will jump to a position. Okay. So to test this multiple submission runs, for example, run, then and runs, for example, this is and runs 100. Then you have to calculate this thing. Okay. You have to calculate all. Okay. For example, this is I, this is I, and set any variable error. Set this value. Okay, and gather all information only for position. Okay, so this will be some head vector like this row column. Okay, set this here column and take the average value. Okay, average value by dividing the total with the total number of runs. So this will be your final output, final statistic output of the error. Okay, when you get the, and this all must satisfy the test. Must satisfy the phi square test. So first you have to check this information and select all those states which satisfy this test. Okay, save in some variable or cell, any cell and matrix cell. Then use this thing in this loop and calculate all runs in this variable, and then take the average value to get the final statistics. So this is your final error output at the end of n scans. Oh, sorry, n runs. Okay. So here all values of this epsilon, this equation, are true or satisfying with this test. Okay. So we said that this is the normalized estimation error squared. So we said that this is a normalized NEES, normalized estimation error squared. So we have normalized this value by calculating the average of the error. And however, your root mean square, you can calculate the absolute value like root mean square as well. But root mean square is not normalized. This is normalized thing. The main difference is two. But many people are interested in calculating root mean square. So you can calculate the root mean square in a similar way. Okay. Your worries because many people use this thing. So in this thing, suppose x is a position and velocity. Okay, this is capital X. Okay, you have already calculated this thing from the Karma filter. Okay, estimated. Sorry, this is the output of the Karma filter. Again, you have to check the this test. Okay. Suppose x is equals to the estimated value of x and the covariance, estimated value of this. So this position and the velocity. So you have to check the position RMS and velocity RMS like root square, like this one, x square and x square is the position, root mean square. You can use this thing for your statistic output at the end of the all run. Okay, and similarly you can use this is for position and this for the velocity. Suppose x dot 1 2 square. Okay. So here function and so you can make a different function. First function is parameter function, second function is initialize, third function is update, and fourth function is this thing, the calculation of the statistic, like this test and this the error, and finally you have to generate the trajectory. So of course you cannot you do not require to generate trajectory for all runs. You can generate only one run, because if you run the trajectory for all runs, all same. Okay. So you can run. So you can use only first run and generate the trajectory of the estimated trajectory of the estimated value of x. We can plot this thing, okay, by using plot command. Here number of scans and x value, okay, and also you can use hold on and plot the true value x of k. Okay, to see the comparison, to see the comparison between the true trajectory and the estimated trajectory. Okay, so here for the calculation of the statistics error and the trajectory, you can manipulate with a parameter like Q and R. Okay, this thing. Why? Because there are some threshold value for the chi-square distribution. Means if this is the threshold for the 10, then the error this figure is error statistics. Okay, x-axis, y-axis, and it shows the position. So when you use the test chi-square distribution, so chi-square distribution set the probability and set some threshold here. So it sets a 95% probability. That your error cannot exceed this line. Cannot exceed this line. This is your maximum line. For example, 0, 1, and here 10. For example, this is 10. Okay, 1, 2, 3, and 10. And this is the number of scan time. For example, if you have 50 scan, if you set 50 scan, then here 50. Okay, so when your Q is 0, then the filter will have very ideal response because this is noiseless environment. The process noise, this is acceleration. The Q is scalar. The Q is the acceleration of the process noise is 0. Then your system, your model is noiseless. So ideal response. So your error is very negligible, like here. Okay. So you cannot use the 0 value. Okay. Otherwise we cannot. This is an undesired feature of the filter because no system will have a ideal response. If you set here Q, then the error will be under this one, under this line. If you even make it higher, like 3, then still it will be like maybe here. But if you make it even more higher, like 9, then this will be like here. So it overhead your chi-square probability of 95% over here. So this is very long. This is not acceptable. So when you use this thing, chi-square test is usually used to minimize the error. If you set this to some, you can say that this is the distance. You can assume that this test is a distance between the true and the estimated value. If there is a higher error, means both will are very far. So you have to reduce the noise. Okay. So if your RMS value, even this RMS value is satisfying with this test, even your RMS or your error satisfying this test, then it will be like this one, because your process line is very high, 9. Okay? Even though this is the true estimation. So this is the true estimation. You can ask, this is a true estimation. Every calculation is very good. Why is it? This is very high. This is very high because you made a very high process noise. So you have to reduce this thing with 1 or something like 2, then will reduce. If you make it more small, like 0.75, then it will be like here up to 4. Maximum up to 4. So my professor always used this value, 0.75. And this value is used by many other people, many other authors. So this is a very good value, and also the value of the F and Q is already given in the book. This is simple. You can say that this is an identity matrix. Okay, just select this just multiply the velocity. It just F. What is used for? What is use of F? Do you remember what is use of F? Why F is used? What is F? I think so many things have covered, so you cannot remember.
Weight of X. Weight of X.
F is simple transition. Identity matrix, time, identity matrix 0, and this is a vector position 200, position xy position, and velocity x velocity, and 0 velocity y velocity, and this is a Gaussian error v, having Gaussian normalized 0 mean and covariance Q. When this multiplied with this thing, so this will add this will add the velocity in here. This is simply identity matrix with the sampling time. So this will give you x of a, like this will add this thing 215. So output of this equation is this one. Output of this equation is this one. So F is, this is F is used for transition from one scan to other scan.
For xk. For xk.
Xk. This is xk. Again, this value is defined here. Only first value defined here. Parameter xk. Then you have to generate a trajectory using this formula. Okay, because you have to, if you just know the first position, how to calculate the second position. Similarly, if you know the velocity, then you have to add the velocity here. Then you can automatically calculate the next position. So this is simply the and matrix which add the velocity, which add the velocity in here to get the next position. If the y velocity is 12, then this will be 212. Okay. So here h q is given in the book. You can see h is also similar identity matrix. We just select the position. If you multiply, if this thing is multiplied with the h rate of k, then what is the output? This h is this thing. Okay, when you add this thing, this will select multiply or 0 multiply with someone with the velocity vector. Velocity vector will be 0. Only position vector will be choose. This will be, if this is 4 by 1, then the output of this thing is the 215 and 212. So h is used for measurement selection, and f is used for propagation or transition of the state to the next time state. Q is a fixed. R is your again sensor noise, and Q is your plant noise, which is your target model noise. Okay. Clear? So if you have understand this method, then you can apply this method to many applications. Many applications like movement mapping, traffic control, air traffic control, everything. And you can use this book and this book. Okay. So this is very important for your study and for your research work. And if you are interested in the sonar signal processing, then this type of estimation algorithm is very important. So before the mid exam, if you have any problem, any programming, then you can come to my office. Okay. So today's lecture was about multipolar summation run. Okay. But I have covered this lecture here because I want in the assignment and in the exam Is the recording start?
Yeah.
In the main exam and assignment, when you generate the results, okay, so develop three figures. Develop three figures. The first one is a trajectory. Suppose this is the trajectory, true and estimated. Okay, and scan and x y axis. This is figure 1, and check for q equals to 0, q equals to, this is figure A, figure B. Make it 3.75 and C 9. So in figure 1, 3 parts with Q is 0, Q 0.75, Q 9. And figure 2, if this test is less than test, then count 1, 2, 3, how many times it correct, how many times correct, means suppose true, track and scan, I scan equals to true track, I scan plus 1 semicolon. So you have, if this is if and if this is true, then add 1 to this scan and make this variable true track. Every time when this test satisfy, then add 1. Okay, then generate this figure here, number of true track. Okay, here you can observe that how many times chi-square test is satisfied. Okay, number of times that chi-square test satisfied. Again, this is a x-axis and scan for level 50, for example 50, but you can reduce as you wish. Okay, you can make it 36, 30, 45, any value, 100, any value. Okay, and this is y-axis. This is the amplitude of this axis will show the number of cube, right? Okay, so the trajectory will be like this one. The trajectory should be like this one. the output should be like this one. This will show that at time here 45 scan, the due number of drag is suppose this value. Okay, and figure number 3 is the statistic error. Okay, and this is in the meter, because the position error, and here number of scan like 50, and for the chi-square, if you have use this chi-square distribution and check for 3 values, for those values like A equals to 0, Q equals to 0.75, and Q equals to 9, A, B, C. This is the error which satisfy test. To satisfy the test, you have to generate those estimated value which satisfy the test. So you have to develop 3 types of figure in the main exam and in the assignment. So
what about Q in figure 2?
in figure 2, the one figure only.
Q
Not because as you know, this is good value for algorithm. This is just for testing, for your purpose, for your learning. So this figure, in this figure, the Q is 0.75. Okay, this is one time. This is for just your learning. So whether Q is 9, the error is higher or lower. This is for your learning. Okay, and also I test you whether you have understand or not. So yeah, this is only one figure.
and can choose test value.
Test value actually, as I already mentioned, it depends on the motion of the target, and so if you set this vector x equals to 200 or any position, not necessarily the 200, you can set 50 and 20 like this. X position 50, Y position 20, but velocities are higher, like 15, 12, and your luxury velocity is 25. Okay, and also your area is 1000 by or 800 by 800. The surveillance area, then test equals 20. Okay. So, but is equals to 50, 20, and the velocity is very small, like 1.5 and 2. Velocity very slow. Then the trajectory will develop very slowly. Here, like here. At the 50 scan, your trajectory will be up to here. Because the velocity is very slow, it will take a lot of time to arrive here. You cannot go far away. It's a very slow process. And then your test will be 1, because at each scan the difference between scan number 3 and scan number 4, the difference is very small. It's very small because velocity is very small. Every time the x of 2 will be like 51.5 and 22. This vector 1.5 and 2. And similarly x3 is 53 and 24. So the difference between each scan trajectory is very small. Then you can make very small test like 1 or 2. Okay? Because the target is very slow run. So then when you are tracking, your estimated value will also go very slow. So due to small difference, you have to make the small value. So again, it depends on you. So I suggest you to start some work, like at least initialize the track, and or at least read this book. If you do not have time, because maybe you have another research work, and also your supervisor maybe have given you some work, so at least you have to read this book. Then if you have any problem, then you can ask before mid-exam. Okay? So the deadline is this one and this. Okay? So I will end the class here.